Swayam Prabha. Digital India. Educated India.
We are back into our lecture series on advanced hydraulics. So, we are in the third module, varied flows. In the last class, we discussed on we introduced you gradually varied flow. So, we also suggested you what is meant by gradually varied flow, where they are seen. We also discussed on developing the conservation equations, especially the conservation of mass equation was already developed to you. Conservation of momentum equation we started, and we suggest it will be completed today, the conservation of momentum equation, and we will see that we will continue on those aspects. If you recall the conservation of momentum equation, we developed it from the general Reynolds transport theorem. So, we had discussed all the terminologies of these equations earlier also, and as we suggested that the flow is predominantly one dimensional, we are just going to consider only the momentum. You know that the net change of momentum with respect to time is equal to the net force acting in the control volume. So, therefore, this quantity was given as sigma f x, and if you recall them, the net forces acting on the control volume were pressure forces on the left side, pressure forces on the right side, the component of gravity aiding the flow, then the frictional forces. These things we have suggested. If you we have also seen that the component P 1 minus P 2, it was derived in the last class. It is rho g cos theta into A 1 y 1 bar minus A 2 y 2 bar, that is for any cross section. If this is the centroidal area, that is the depth to the centroid from the surface, if it is y bar, and if this area is A, then A y bar is equal to moment of area with respect to the surface. This we have discussed earlier. So, we have two cross sectional areas on the downstream, that is on the upstream, that is section 1 1, downstream section 2 2. So, therefore, P 1 minus P 2 are derived on this way. We suggested that for the frictional forces F f, to obtain the frictional forces F f, one need to understand the shear stresses acting on the boundary surfaces of the control volume. So, if you recall in the uniform flow also, if you recall in the uniform flow, we have seen that average shear stress in uniform flow, while deriving the chassis equation, it was given as rho g A by P into S naught. If you recall them, the average shear stress was given in of the following form. The same quantity will now be applied here. Now, instead of the bed slope here in the non-uniform flow or in the gradually varied flow, we will be using a new term called shear slope. So, we will be using a new term called shear slope, and we will be incorporating them in the average shear stress equation. So, the average shear stress in the gradually varied flow can be given as rho g r S 2. So, this average shear slope, how do you how do you compute shear slope? So, in the uniform flow, your bed slope, your water surface slope, the energy slope, all were same, all were equal, means there were no changes in them. Therefore, you were able to use the bed slope in computation, the Manning's equation and all, you could directly incorporate bed slope, and even the bed slope was computed, if you recall them, I hope it is that the bed slope in shear bed slope in uniform flow it was given as Manning's roughness coefficient, square of Manning's roughness coefficient is squared r to the power of 4 by 3. If you recall this equation, the same equation now we are going to incorporate to calculate shear slope in gradually varied flow. So, shear slope is seen only in non-uniform flow. So, in uniform flow you do not have the concept called shear slope. So, here the shear slope S2, we will be using the same Manning's equation and you will be computing the following thing, n squared q squared s squared r to the power of 4 by 3. So, this also it is also called friction slope. So, in some of the literatures you may see these terms friction slope. Therefore, force due to friction or boundary shear, I can give this as F. This is equal to shear stress into the wetted perimeter into the length. Just recall the figure. Our channel bed is like this, two sections, control volume. If they are, the two sections are separated by a distance del x, this is having depth y1, y2, then the wetted perimeter P into del x, that will give you the area where the water is interacting with the surface, with the channel boundary. So, wherever water is interacting with the channel boundary, the friction force will be encountered, and that friction force is given by shear stress into the wetted area. So, this is nothing but your wetted area in the reach. Okay. So, I can now suggest that, or if let me for your benefit again, if you can't visualize the thing, just consider the two sections of the channel. Now, these are the wetted areas, and if this length is del x, and if the for any of the cross section the wetted perimeter is given by the following form. So, P into del x, that will give you the wetted area. So, the same thing we have incorporated. So, the net force in the x direction, please recall that the flow is one dimensional. So, it is given as P1 minus P2 plus W sin theta minus FF. So, P1 minus P2, you know what is that? It is rho g cos theta. Theta is the angle of the bed of the channel with respect to horizontal. A1 y1 bar minus A2 y2 bar plus W sin theta minus rho g r into S2 del x. So, let me draw the channel reach again. So, in this channel reach, the control volume whichever you are taking into account, if the upstream area is separated by a distance del x, if they are separated by a distance del x, say if we are suggesting that the upstream area is A, the depth of flow in the upstream if it is y, the depth of the centroid in the upstream if it is y bar, then you can also suggest now the following quantities. At the downstream, you may give A2 is equal to nothing but the upstream area plus dou A by dou x into del x, because this area it is varying with respect to x only, that you know, that means the change in area, this is the property of x in the flow direction. Similarly, y2 can be given as y plus dou y by dou x into del x, or you know that y is varying only with respect to x. You can write this as y plus dy by dx into del x. Similarly, one can also suggest the quantity A y bar if we take into account the moment of the area. So, A y bar, this can also be given as, say, in the section 2 is nothing but A y bar in the section 1 plus dou by dou x of A y bar into del x. Like that also one can easily give, isn't it? Because you have seen in the sigma fx equation, this is rho g cos theta A1 y1 bar minus A2 y2 bar, right, or I can say P1 minus P2. So, this quantity now can be easily substituted, A2 y2 bar can be easily substituted here. So, I can write it like this now, A2 y2 bar is equal to A y bar plus dou by dou x of A y bar into del x. So, on using these relationships, you will see that the net force in the x direction, it can be now written as rho g cos theta A y bar minus A y bar plus dou by dou x of A y bar into del x plus w sin theta minus rho g A S2 del x, right. So, why we need to write it like this? In the previous slide, if you recall them, I think I made a mistake in the earlier slide. If you see here, this is rho g r S2 into P into del x, that is the So, please correct it, this quantity rho g r S2 P into del x. P into del x is your wetted perimeter. So, you have to incorporate this quantity. Means, so, I have made a mistake there. So, you correct them. So, that P into R, that gives you the area of the cross section A. So, I have directly incorporated A here. So, in the equation, sigma f x is equal to eta rho du plus v dot n dA. If you recall this equation, now one can write that as the flow is steady state, this component in the equation, it will vanish off. Therefore, you can write now outflux rho v squared dA minus influx rho v squared dA. So, what does this mean? So, what does this mean to you? As you take any arbitrary cross section, say this is section, it is having area A. If the average velocity is v, the quantity this quantity, that is the areal integral, that is why we are giving it areal integral in that form. So, the areal integral, one can now write this quantity, because rho v squared dA, you know that this is not the average velocity, this is only the velocity at any point in the section. So, this quantity now can be represented in the form of average velocity v squared into A, but they are not same, because you know the momentum, this quantity signifies the momentum flux across this control surface or across this cross section. What is the momentum flux transmitted? So, the momentum flux integral rho v squared dA is not equal to the average quantity. If you take the average velocity into A, that momentum flux or whatever momentum flux you obtain through the average velocity, that will not be same. So, you need to means you have already seen them, you have incorporated momentum correction factor. Earlier. So, that momentum correction factor beta m need to be incorporated here, and subsequently we can address the issue here. So, this is the above quantity now will become outflow rho v squared dA minus inflow rho v squared dA. This can be now easily written as minus beta m rho v 1, that is the average velocity in the section 1. That is why I put the bar here, V 1 bar squared into A 1 plus beta m rho V 2 squared A 2. So, we are taking the momentum correction factor throughout almost same. So, beta m and rho can be taken out in this expression. So, you will get this is equal to beta m rho V 1 squared A 1 plus V 2 squared A 2. So, as again mentioned earlier, at section 1 V 1 bar we are taking it as V bar, A 1 we are taking it as A, depth of flow y 1 we are taking it as y, the centroidal depth y 1 bar, this was being taken as y bar. We have done it earlier also. The same quantity we can same relationship we can subsequently incorporate it here. You will see that V 2 bar is nothing but V 1 bar plus dou by dou x of V bar into del x. That is the separation, the change in velocity as it moves in the x direction is given by this thing. This is the velocity in the section 1 and this is the change in velocity as it traversed a distance del x. So, that relationship can be given here in this following form. Now, you can also give the following thing. The following product V 2 squared A 2 is nothing but V squared A plus dou by dou x. All these quantities we are using the same first principles. So, there is no much complexity involved. We are suggesting that this entire quantity, it is being changed using this relationship as it goes from upstream to downstream. So, this relationship also we can incorporate. So, we will get the following equation now. Rho V squared dA, this is equal to beta m rho V squared A plus dou by dou x of V squared A del x minus V squared A equal to beta m rho del x dou by dou x of V square A. So, you know beta m is the momentum correction factor. Also Q is a constant quantity V bar A. Therefore, net change in momentum fluxes across the control volume, across the control surfaces of the volume, this is equal to beta m rho del x dou by dou x of Q V bar. I hope you agree in me writing this thing. Or again, one can infer V is equal to Q by A, like this also you can infer. Then I can change this quantity as beta m rho del x. Q is a constant value, so Q squared I can take it out, and this is dou by dou x of 1 by A. Well, fine, can easily write it. So, you can write this quantity. Now, you can see that dou by dou x of 1 by A, this is nothing but 1 minus A squared dou A by dou x, or you can also see that 1 minus 1 by A squared dou A by dou y into dy by dx. Like this also you can write. Recall our earlier lectures, dou A by dou y, throughout we have given this as the top width of the channel, top width of the flow of the channel. We have been dealing it in almost all of the classes. So, that same thing I am going to adopt it here. So, dou by dou x of 1 by A, this is nothing but minus 1 by A squared T dy by dx. Therefore, net momentum flux change is equal to, see the negative quantity has appeared here. So, I have to incorporate that here, minus beta m rho del x q squared by A squared T dy by dx. So, come back into our net force in the control volume. Net force in control volume sigma Fx, this is equal to minus rho g cos theta, or let me show you that equation. So, sigma Fx is equal to rho g cos theta A y bar minus A y bar plus this entire quantity. So, these things gets cancelled off. So, I can use the remaining terms minus rho g cos theta dou by dou x of A y bar into del x plus w sin theta minus rho g A into the shear slope S tau into del x. So, you know w sin theta is nothing but rho g to area into del x, and the slope sin theta. What is sin theta? It is nothing but your bed slope S 0, directly incorporate. Yeah. So, therefore, your sigma Fx is nothing but rho g into A del x S naught minus A into S 2 del x minus cos theta dou by dou x of A y bar into del x. So, again rearrange the terms here. You will see what can you get here now. Sigma Fx, simplify the terms, all the things. You will get a very good expression now. Rho g del x A into S 0 minus A into S 2 minus cos theta dou by dou x of a y bar. So, dou by dou x of a y bar, we have already seen that earlier. Substitute those quantity now, what will you get? You see here, I can take the quantity now as sigma f x is equal to minus beta m q squared by a squared t dy by dx is equal to rho g del x a s 0 a s 2 minus cos theta dou by dou x of a y bar. So, you can cancel rho as it is an incompressible liquid and all. You see that rho has come out, you can cancel them. You can also take a out from here, you can incorporate it here. You will get means very good relationship now. I can easily write now this as S0 minus, that is the bed slope minus the shear slope, this quantity minus 1 by a of dou by dou x of a y bar cos theta. This is nothing but equal to minus of beta m q squared t by g a q. So, I hope you remember this particular term q squared t by g a cube, you have seen in some other portions also. So, how the terms they are all coinciding, how they have, how the physical significance are coming into picture. I hope you are getting it clear now. So, like this equation is obtained. Again I can rearrange them. S0 minus S2 is nothing but equal to 1 by a dou by dou x of a y bar cos theta minus beta m q squared t by g a q dy by dx. Let us see what is the term dou by dou x of a y bar, this particular term. This I can now write this as a y bar into dy by dx, the differentiation rule. Dou by dou y of a y bar, what it could be? As we are mentioning it earlier also, this is moment of area with respect to the water surface. So, if you have the section like this, if you have your cross section and if this is the area A and the centroid of this area is y bar. So, a y bar is the moment of this area with respect to the surface of water. So, if the surface of the water changes, say if it increase by a height del y, say if it increase by a height del y, then how that change is incorporated in this thing. So, that can be used for getting this particular different derivative dou by dou y of a y bar. So, I can write this as now dou by dou y of a y bar is nothing but as limit del y tends to 0 a into y bar plus del y plus this is the top width t, this width is t. So, t into del y by 2 minus A into y bar, that was the previous area, moment of the area, if you recall that, divided by del y. So, as limit del y tends to 0, what happens to this quantity? A y bar gets cancelled off, and A del y term remains, T del y squared by 2 also remains, 1 del y is already cancelled off. So, and del y is tending to 0, you will get this quantity as the area A itself. So, wonderful. We can now directly write this dou by dou x of A y bar as A into dy by dx. Now, I can write it this directly. So, what happens to our momentum equation? S 0 minus S 2, S 2 is equal to cos theta into dy by dx now, minus beta m q square t by g a q dy by dx, or your dy by dx, this is nothing but S 0 minus S 2 by cos theta minus beta m q square t by g a q. So, this is the most fundamental equation in the gradually varied flow. What is the physical significance? What did I obtain after all this derivative, after all these derivations, whatever we have done here? What is the thing you are obtaining? You are obtaining the quantity, the slope of the water surface. So, please recall gradually varied flow. What is meant by gradually varied flow? Gradually varied flow, we suggested that the surface, the depth of the water decreases or increases gradually as it flows from upstream to downstream. So, that change in the water depth of the water surface, the depth of the water, that is signified by this particular quantity dy by dx. So, it also signifies the change in slope of the water surface. So, that quantity is obtained by the following relationship. This is the most fundamental equation in the gradually varied flow. So, if you have to solve any gradually varied flow problem, you have to solve this equation. It is also called the dynamic equation for gradually varied flow. This is also called dynamic equation. Why it is called dynamic? That is, this is a gradually varied flow equation. The gradually varied flow equation as described above, it is also called dynamic equation for the only reason that this equation was derived using momentum conservation. We have developed it using the equation of forces. Therefore, this is called dynamic equation. You can also suggest it as a differential equation for gradually varied flow. We will see what happens if you use the conservation of energy. So, I am not going to go deep into this portion. Conservation of energy, if you use control volume, conservation of energy. So, I can write the equation now dE by dt as dou by dou t of beta rho v dot n dA. So, their extensive property B is now equal to the energy of the system or energy in the control volume, small beta the corresponding intensive property, all those things club. And as the flow, you know that the material derivative of energy, then it will be 0, that is energy can neither be created nor be destroyed. And another case, as this is a steady flow condition, this quantity will also the left hand term will also is also a 0, and the first term on the right hand side, that is also 0. You will get the following relationship now. that is this particular quantity, it can be given as, in the inflow section, the intensive property, this thing is given as P by rho plus Gz plus V squared by 2 rho V dA. This is equal to, in the outflow section, P by rho plus Gz plus V squared by 2 rho V dA plus rho G Q into the head loss between the two sections, sections 1 and sections 1 and sections 2 2. So, Q is the steady discharge, del HL is the head loss. It is also called the mechanical loss of mechanical energy per unit weight. So, consider the section, any portion, any reach. If this is the water surface depth, then generally we give this as the y, depth of flow y. This particular quantity, the vertical portion, it is y cos theta. Say if you are considering any datum line, then the bed at this location, it is elevated at a height z0 from the datum, and if you want to measure any quantity from the bottom, as we have seen earlier, you can suggest that, say for this point, particular point, this is now say y, it is y dash cos theta. Let us give it in that form. So, y dash cos theta, one can easily suggest that pressure at that point P, as earlier we have seen, rho G into y minus y dash cos theta. Your datum head of that particular point, this particular point, that can be given as z. So, that z is equal to z0 plus y dash cos theta. So, what do you get from these things? You will see that from these two relationships, P by rho, this is equal to G y minus y dash cos theta, and G z, this will be equal to G z0 plus G y dash cos theta. So, therefore, P by rho plus G z quantity, I can easily write, just add those things. I can easily write this as G y cos theta plus G z 0, other terms gets cancelled off. So, you can get these things. Why I have written is that, if you recall in the section A1 in flow, you had that this particular term P by rho plus, that is the intensive property in the equation. So, we got this term. So, rho V dA, this can be easily now written as this entire quantity for the section, it is matched now. So, rho G, it is rho G, rho is taken out of the integral, rho G z0 plus y cos theta, okay, y cos theta. If you integrate it aerial V dA, that will give you the discharge Q. So, that I have just incorporated it here. Now, there is another integral, integral aerial integral V squared by 2 rho V dA. So, what is that quantity actually? So, I have to write that here, aerial integral rho V1 cube by 2 dA. So, in the next we can see rho g z0 plus y cos theta q plus integral a1 rho v1 q by 2 dA. This is not will be equal to, in the right hand side, z0 plus why I am writing is that, just recall the earlier section. So, if this is the right hand side, so this bed slope, this z0 in the upstream, z0 in the downstream, if it is changing by this quantity, I can write it like this. So, plus y plus dy by dx into del x cos theta into q. Then you have the areal integral rho v q by 2 dA plus rho g q del HL. So, this becomes the energy equation becomes in the following form. So, this particular, if you see in these two equations, in these two particular terms, this quantity, it is an areal integral, this quantity is also an areal integral. So, you need to take into account the energy correction factor alpha. You know that energy correction factor, you have to employ them. So, I can then write the following quantities: any integral rho v cube by 2 dA is equal to the kinetic energy, the energy correction factor rho into the area into the average velocity, like this. Like this you can write them. So, both the places you write them, you will get the following relationship now. So, I can write the thing z0 plus y cos theta plus alpha v squared by 2 g. This is equal to z0 plus dz0 by dx del x plus y plus dy by dx del x into cos theta plus alpha by 2 g v squared plus d by dx of v squared into del x plus the head lost. So, all the terms are in units of the length. So, these are the energy per unit weight terms. So, you can get it in this following form. You have the elevation head, you have the pressure head, you have the velocity head in these things, and we know that d0 by dx is nothing but the bed slope as 0. I had to give it minus because it is decreasing. The elevation of means the value of z0 is decreasing. Also, the quantity d by dx, d by dy of v squared, what this will be? You know v squared, that is q is equal to v a, right, or v is equal to q by a. One can easily identify that. So, substitute that quantity here. You will get this quantity as d by dy of v squared is equal to minus 2 q squared t by a cube. The quantity del HL by del x, that can also be obtained here. it is given as the energy slope. So, one can easily use this thing now, rearrange the terms. You will get dy by dx is equal to S0 minus Se by cos theta minus alpha q square t by g a q. So, again I got a gradually varied flow equation now using the energy equation. So, you can use both appropriately, whichever circumstances, according to the circumstances you can use both the equations. The quiz for this lecture is, the first question to you is the conservation of mass equation for gradually varied flow between two sections 1 and section 2. It can be derived. You have derived this in this class today. So, you do that derivation again and show it to me. The second question for the quiz is, what is the dynamic equation for gradually varied flow using conservation of momentum principle? Explain the terms in the equation. So, I am repeating the question, what is the dynamic equation for gradually varied flow using conservation of momentum principle? Explain the terms in the equation. The third question for this quiz is, what is the dynamic equation for gradually varied flow using conservation of energy principle? How is it different from the one derived using conservation of momentum principle? I am repeating the question, what is the dynamic equation for gradually varied flow using conservation of energy? How is it different from the one derived using conservation of momentum principle? So, the solutions for this quiz are, the first question you are asked to derive the conservation of mass equation for gradually varied flow between two sections 1 and 2. There is a, if there is a gradually varied flow between two sections 1 and 2, you were requested to derive the continuity equation or the conservation of mass equations. So, from the basic Reynolds transport theorem, if you recall them, we had suggested that the change in mass inside the control volume between the two sections plus the net outflow of mass across the control surfaces of the control volume, this should be equal to 0. It has been derived, I means it has been already told to you. From this thing, it is now, as it is suggested that gradually varied flow is steady, therefore, this component vanishes off, right. So, you can now suggest that the equation remains as rho v dot n dA is equal to 0. From the control volume, two control surfaces allow flow across through that, and that is the plane normal to this section 1, plane normal to the portion 2 here. Only those two sections allow flow across through those planes. So, you can now easily write this thing as the flow is incompressible, you can remove rho also. So, that is, you have two sections, here one section is there, here another section is there. So, minus V 1 average velocity into A 1 plus V 2 A 2 is equal to 0, or V 1 A 1 is equal to V 2 A 2 is equal to your discharge Q. So, this is the conservation of mass or continuity equation for gradually varied flow. So, the solution for the second question, you were asked what is the dynamic equation for gradually varied flow using conservation of momentum. We had derived those equation, if you recall them. The slope of the water surface dy by dx is equal to S 0 minus S 2 by cos theta minus beta m q square t by g a q. So, dy by dx is the slope of the water surface, S 0 is the slope of the bed, S 2 is nothing but shear slope. We had discussed those things in the last class. Q is the steady discharge, T is the top width, A is the area of cross section, theta is the angle at which the bed or the channel bed is having with the horizontal. That is, if this is your channel bed, how much angle it is making with the horizontal line, that is theta, that is the angle theta. So, all the terms are self explanatory. The third question asked to you was, what is the dynamic equation for gradually varied flow using conservation of energy. So, this was also derived. Again, dy by dx is equal to S 0 minus S e. Please note the difference, cos theta minus alpha q square t by g a q. This is the dynamic equation for gradually varied flow using conservation of energy principle. So, you can see that this is quite different from the one developed using momentum principles, S 0 minus S 2 by cos theta minus beta m q square t by g a q. There are similar terms, but there are some differences also. Here in the momentum equation you had used shear slope S 2, whereas in the energy equation you have used the energy slope S e. For the kinetic for the energy for the correction factors, you had used the kinetic energy correction factor in the energy equation, whereas you use the momentum correction factor in the momentum equation. So, that is alpha and beta m, those differences are there. So, therefore, they are not the same. In principle, they are different, because kinetic energy correction factor and momentum correction factor, they can differ for any channel section. Similarly, the energy slope as well as the shear slope, they can also differ. Thank you.